Digital Capture to Image Output by Mark Struthers. A digital image is not an exact snapshot of reality. It is only a discrete image in time. We'll explore how the interaction of energy with tissue from different modalities is converted to a visual image for display. Here we see an analog capture turned to a visual display. To create the display from analog to digital conversion, what we'd start with is the analog signal. We then sample this signal and change this to an analog to digital conversion. When we want to visualize this, we reverse the process. We create a digital to analog or visible light image. Energy is absorbed by the digital detector and transformed into electronic charges. These electrical charges are recorded, digitized, and quantified into a grayscale that represents the amount of energy deposited on the detector. The grayscale is then mapped to the monitor, creating the display image. Post-processing software is needed for organizing the raw data into a clinically meaningful images. The images are sent to archive and linked to patient demographic information and then sent to a workstation for review. First, we notice the interaction of X-ray with tissue and the absorption of the energy within the tissue. This creates remnant radiation to be recorded at the image receptor. This acquired energy is then mapped onto a grayscale matrix that represents the image that we have obtained. The resulting image is due to subject contrast. Subject contrast is the difference in some aspect of the signal prior to its being recorded. It represents the patient's anatomy and/or physiology. The probability of X-ray interaction with matter depends on initial energy of the photon, the density values of interest of the imaged area. This is comprised of the thickness and atomic number of the tissue, the amount of photons available from the X-ray tube, and anatomical information from the varied interaction across anatomy. Each of the tissues in our body has a different amount of water, which creates different densities. Here is a listing of some of the different tissues in the body, their atomic number, and the density that they represent. It is obvious that there is not a great variance in the densities of the tissues, and therefore we end up having to post-process the data that we have acquired. Medical images have the 5 specific quality characteristics of data. They are spatial resolution, contrast resolution, noise or signal, detail, and artifacts. Collimate to the area of interest. Do not use post-processing masking as a substitution for collimation. Collimation, positioning, and exposure are critical. Once the area of exposure has been localized, a histogram analysis of the exposed area can be undertaken. We begin by recording the brightness. All pixel brightness levels within the anatomy of interest should be neither completely white nor pitch black, but should possess an intermediate shade of gray along with a broad range from very light to very dark. We need to look at the contrast and grayscale, which should be balanced such that a number of details present in the image is maximized and there is sufficient visual differentiation between adjacent details. This is a difficult one, signal to noise ratio. The signal is our exposure. Do we have enough signal or do we have too much signal? Maximum signal-to-noise ratio must be achieved in every image by maximizing penetration of the signal to reach the image receptor and minimizing quantum model, electronic noise, and scatter of radiation in all other forms. Spatial resolution, or the number of pixels that are demonstrated in the image, is extremely important. We need to look at our matrix size and pixel size for detail. Spatial frequency, or detail, is usually measured in cycles or line pairs per millimeter. Resolution is a measure of how well details are preserved. Spatial resolution is the ability of an imaging system to resolve and render on the image. The final image has good detail and contrast and brightness so that you can differentiate between the different anatomical areas fairly easy, even when they are close to one another. That is, close in proximity and close into shades of gray. Now we want to take a look at contrast. Remember, a digital image is not an exact snapshot of reality. It is only a discrete approximation, and the contrast makes a big difference in the images that we view. Contrast is the difference in the image grayscale between closely adjacent regions on the image. Contrast present in a medical image is the result of a number of different steps that occur. These steps occur during image acquisition, image processing, and image display. In imaging processing, we start with acquisition, then pre-processing, and finally post-processing. All modalities capture imaging data that can be processed into an image. In pre-processing, there are two major things we're going to look for. We're going to eliminate any detector flaws and also control the dynamic range. A digital image is not a film screen image. Therefore, we lose the visual cues that we once had with film screen. Digital images also have a very wide dynamic range, or the number of shades of gray. The image that you see on your modality screen after capture is not the original image, but an image that has been automatically rescaled by image processing. Simply stated, the computer, the modality, has taken the data that you captured in your exposure and altered that data so that it appears like the image that you requested originally. This means that in imaging processing, the relationship between radiographic factors and appearance of the image are decoupled. The controlling factors do not have the same impact on the image. Mass does not equal density or brightness, and KVP does not equal contrast. Those are controlled mathematically through adjustments of contrast and brightness algorithms on the computer. The data contained in a digital image can be displayed as a histogram, which is a plot of the pixels values ranging from black to white versus the number of pixels that have that particular value. The display values of those pixels, or how they will appear on the viewing screen, is determined by the display curve. In the histogram to the left, a pixel value of 68 would have a display value of 68. The display curve is straight with a slope of 1. The straight line over the histogram demonstrates the original or unprocessed raw data. That is our original image capture. By placing the straight line portion of the H&D curve over the histogram, we're able to manipulate the image, showing what we consider to be a normal chest X-ray. Moving the straight line portion of the H&D curve to the left causes darkening. And if we move it to the right, we get a lightening effect like an underexposure. This represents data manipulation. Now let's see how the computer automatically rescales your image if it's an overexposure. We see the actual exposure, the overexposure, and we're going to reduce the amplification to make it appear to be a normal exposure. If we use an acceptable technique range, this will be no problem. But what happens when we overexpose or underexpose beyond an acceptable technique range? Underexposure means we just don't have enough signal, and that can cause quantum model. On the other hand, overexposure will be too much signal, and what that will do simply is to darken the image and lose detail. This means that exposure technique is still very important. We need to get the right exposure. The advantage of digital information is that each location and nature of each digital level are known and can be adjusted, and this is why it is important to understand processing. Each image can be corrected by simply adjusting the brightness so that the H&D curve moves back over the peak that represents the anatomy, and the slope of the curve can be adjusted for contrast. The image detector also happens to affect contrast, dependent on the type of detector it is and the size of the detector electronics that are acquiring the data. When viewing the data at our modality, we should look for geometric invariance. The image should preserve the geometry and the relative size of the image. Check for contrast invariance. Prior to post-processing, the image should preserve the luminance values of objects in the image and the overall contrast of the image. We want to assess the image for noise or underexposure, and we want to look at the edge preservation. The image should preserve edges and boundaries, sharpening them when possible. Aliasing. That means that the image should not produce a jagged or stair-step edge. Texture presentation. What this means is you should not use a filter to smooth or enhance the image before you post-process it. And finally is modality awareness. The image created should be appropriate to the type of images and orders of resolution for that particular modality. There are many types of contrasts that go into creating an image. The first being the acquisition and the contrast inherent in the detector that is acquiring the image. How many pixels and how much resolution is available. The other thing we look at is the imaging technique used to create the energy. And the third thing is the body habitus, which is subject contrast. Subject contrast is the difference in some aspect of the signal prior to its being recorded. Subject contrast is the result of fundamental mechanisms, usually an interaction between the type of energy used in the modality and the patient's anatomy or physiology. For example, in X-ray, we're recording radiation, and in MRI, we're recording the radio frequency signals. Instead of pixels, the detector has detector electronics known as DELs. The smaller the DEL, the more DELs you'll have on the detector, and the better the contrast. Here we see the different types of detectors and the light spread for the DEL as in relationship to the number of pixels in the matrix. Each manufacturer vendor varies, but the detector contrast is determined principally by how the detector maps the energy captured by the modality. One of the most powerful attributes of digital imaging is that their displayed appearance can be changed. The appearance of the image can be modified by manipulating the lookup table used to convert or map the digital image residing in the computer to the display hardware itself. Here we see the same data mapped in high contrast and low contrast. There was no need to take a high contrast image or low contrast image like you would in film screen because we're just utilizing the data. We're all aware that if we change technique factors, we can actually change the contrast and density and how the image looks. There are a lot of other factors that are included that can be changed, with contrast and brightness and a histogram, but we'll go over that later. What I want to do first is have you take a look at the effects of independent control and detail contrast. Images in each column have contrast and latitude, but detail is reduced from top to bottom. Images in each row have contrast detail, but latitude is decreased, moving from left to right. Modern digital equipment will automatically rescale your exposures to show something that appears to be the correct exposure. As long as there's enough signal to choose from to match the lookup table or what you want the image to look like, you have no problem in getting the exposure rescaled. Does this mean you can use any exposure? Well, certainly not. What you're looking at is if you don't have enough signal, you're going to get quantum model. And if you have too much signal, you're going to lose detail. Now, let's take a look at how this actually works. Here we're going to see an overexposure has been acquired. That's not the exposure we want, so we scale it down to the correct exposure. This method of automatically adjusting displayed brightness and contrast in digital medical imaging is an adaptive histogram equalization. The adaptive equalization is not like an AEC, it simply adjusts the image. Remember, each pixel of the matrix has only one color or one shade of gray. If we have to adjust that, it is an incorrect exposure. You may be able to see quantum model if you're underexposed. If you're overexposed by 300% or more, you may not be able to get the equalization done by the computer, and you'll notice a lack of detail in the darker areas of your image. Here we can see that matrix size determines the resolution and bit depth determines the contrast. We have a histogram over here that is of the same image, but as we move the H&D curve over the histogram, we change the look of the image. To move the H&D curve over the histogram, we are adjusting either the contrast or the brightness of the image. Here's a little exercise I had with my class back in 2010. Wow, a long time ago. And this is when we were using S numbers. But the point is that we had our mannequin and we ended up with an exposure that looks like a great exposure, except for the problem of our feedback from the computer. What did our feedback basically tell us? Well, the S number is 48 and the latitude is 1.77. This means we're way overexposed. Today we have EI numbers, exposure index numbers, and DI numbers. But what we're looking at here is the image as it was actually acquired. Now let's watch the computer go ahead and take that and turn it into an acceptable looking image. So now we can just go ahead and send it for reading, right? Wrong. The gross overexposure shows that we may have missed some data. That data might make a difference in getting a diagnosis or not. Now, what if you don't have any choice? Here's the original image. It's a supine AP chest x-ray on a very large patient. You can see it's all the way grayed out, but let's say we could not get back into the room to take another chest x-ray on her right away. Could we have this as the original and still manipulate the data to try to get some information to the radiologist? Let's see what we can do. Does it look a little better if I increase the contrast by 40% on my window and level? What happens if we increase the brightness a little bit as well? Does that change the image? By increasing both the brightness and the contrast, we have quote-unquote improved the image a little bit, but we didn't have a whole lot to start with, but it is better than the original. So the advantage of digital is that it can optimize image quality by manipulating digital data to improve visualization of anatomy and pathology after exposure to the patient. So when we're looking at this from a physics standpoint, if we sort by pixel location, that results in a matrix. If we sort by pixel intensity, that results in a histogram that we would map to the matrix. And sorting by object size results in a frequency distribution that we map. So remember, when we have rows and columns together as pixels, that's the matrix. The number of shades of gray that we can see is called the bit depth. The larger the bit depth, the more dynamic range, the more information we can actually show. So we've got our matrix where we're going to map to, and we've got the shades of gray that we're going to map. How we would do that? We do that by the intensity. And this is where we map the intensities or frequencies. Here's another example. We look and it looks pretty good on our monitor, but we still didn't look at the EI exposure index number or the S number. And when the radiologist gets it, he wants to magnify it. And guess what? It was underexposed. It has quantum model. So we begin to see there is a lot to analyze when you're looking at your image. Not only do you look at the image on the screen, but you have to be able to analyze the information that is coming with the image to see if it is a good quality image, because the computer is trying to make it look like what it should. So just looking at the image for collimation and positioning is only half the battle. You need to look at the whole picture. A digital image is displayed as a combination of rows and columns known as a matrix. The smallest component of the matrix is the pixel, which is a contraction for picture element. The location of the pixel within the image matrix corresponds to the area within the patient or volume of tissue referred to as a voxel. The voxel gives us depth and many shades of gray, but each pixel, which is only the two-dimensional image, not the three-dimensional, just two on the matrix, gives us only one color or one shade of gray. There can be no gradients, there can be no other thing there except one color and one shade of gray. We get the shades of gray by measuring the voxel or the depth. The intensity of the radiation that is measured gives us our spatial domain for the pixels, or how we actually map them. They have to correspond to the body that they went through. In the intensity domain, pixels are sorted by their pixel value, which is brightness and density. But in the spatial domain, they are sorted by their location. Finally, in the frequency domain, the objects are sorted by their size. And the size depends on how big the manufacturer's DELs are. Now let's talk about dynamic range. Really, dynamic range is what we used to look at on our H&D curve when we were looking at the speed classes for the films. Remember that? Well, as we know, there were different things that we would look at. One would be base fog, etc. Well, the dynamic range is that shades of gray and how many shades we can actually see. There's a big difference between the number of shades of gray that you can see well in film screen and the thousands of shades of gray that you can see well in digital. This means we're able to utilize the digital information to create better images. Basically, the mapping function is using the shades of gray or the intensities like we used to use in the old paint by numbers thing. If it has a certain number, you paint it that color. And when you put it all together, you have an image. Same thing. Mapping function tells us what new values to substitute in for each pixel value that results in an image that will have the appropriate look for the anatomic part. Can you change that look? You bet. That's why we modify brightness and contrast. In digital imaging, you're in control just like you are in paint by numbers. Let's go back and see how we do analog to digital conversions once more. The energy interacts with the body, and we sample the energy to change it from continuous into digits, and that gives us the raw data that we can map. The sampling of the signals is stored. We utilize this stored data to create the images. We choose which data to utilize, and we do this using lookup tables. Remember, binary digit is a bit, and one bit has two colors, black or white. 2 bits has 4 colors. 8 bits has 256 colors, and so on. The lowest number of bit depth used in digital imaging happens to be 10 bits. The higher the number of bits, the more accurate the analog to digital conversion will be. We manipulate the digital data changing the window width and the window level, or brightness and contrast. The window width is the control of the contrast or the range of grays the computer is able to display for an image. A wide window width gives us many shades of gray, a long scale contrast, whereas a narrow window gives us high contrast. Remember, most digital images are 10 bits or greater. Here we can see the dynamic range of digital medical imaging systems in bit depths and shades of gray. The only medical imaging system that uses 256 or 8-bit depth is ultrasound. The rest of the modalities go from 1024 bits to 65,536 bits and more. Prior to digital imaging, we used photographic technique or film screen, which had a minimal amount of shades of gray available to create the image when compared to digital. Digital imaging capture gives us a much greater dynamic range or number of values of interest, which contain more information than we did record with film screen. When making an exposure, there is an optimal range to be captured. You'll notice that as we increase the mass, we start to gain pixel saturation, which causes loss of detail. As we reduce the exposure, we'll find that we start to lose the amount of shades of gray that we can record and start to get what is called quantum mottle or noise. Pixel saturation can be described by the fact that no pixel can be darker than pure black, nor brighter than absolute white. As we increase the exposure, we begin to decrease the dynamic range. If you look at this image, you can see that there are more shades of gray and less contrast. Although the image on the right is nice and contrasty, notice how you lose detail. Each manufacturer has their own unique method to correct raw image defects within their processing technique. The goal of this processing is to present to the radiologist a diagnostically useful image with no misleading artifacts in a familiar form. So let's take a moment to look at image processing, acquisition, pre-processing, and post-processing. When we get acquisition, we want it to be compensated or uncorrected raw data. In pre-processing, the raw data is corrected. We calibrate it by taking out dead pixels, alignment defects, correct the shading so we get a nice flat field, and we amplify the signal. Once the manufacturer has acquired the data, pre-processed the data, we then go into post-processing of the data where we actually do enhancement. We do equalization, we look at contrast and detail, we reduce noise, and we apply different advanced visualization techniques. Let's look a little closer at image pre-processing. There are two major steps to correct and adjust for. The first one is detector X-ray system flaws, which can be pixel defects, sensitivity variations, or offset gain variations. The next step is to adjust the detector for dynamic range. We also scale the image data and optimize quantization levels for post-processing. The vendor's pre-processing of the images allows them to correct for any flaws from the detector origin or the equipment origin. In this process, we use stationary patterns for fixed point noise. We adjust the thickness on non-uniformities within the detector. We check the detector for dropout or dead pixels or dead columns and correct those. And we adjust the dark current variation. The dark current is the current that is always on the detector, so we have a homogeneous background. Now we've optimized the data coming in from the X-ray equipment and the detector. We're going to utilize lookup tables for anatomical programming. A lookup table is simply a cross-reference linking index numbers to output values. We know the intensities in the original data are quite flat, so what we want to do is take those intensities and optimize them by matching them to a different brightness to create the image display for the monitor. We use the lookup tables for post-processing. The lookup table processing changes the contrast characteristics of an image by substituting numbers that are different from the original pixel values or the original captured data. In this example, we are keeping it simple and working on an image with only two pixel values, 40 and 30. The 40 and the 30 would be the original acquisition intensities, and we want to change these to higher contrast, so we'll change them to 90 and 10. We have an original lookup table which again has like AP or PA chest. It has all the densities and all of the intensities that we're looking for. But we want to manipulate those intensities and densities. To be able to manipulate the images correctly, we use an H&D curve or an S-type curve which emulates the original look of film screen brightness and contrast. The linear portion of the curve is that portion which will show when we manipulate the data. What we will do here is take a look at the movement or scrolling of the H&D curve over a histogram. And this is done by using the brightness and contrast controls on your equipment. Built into the equipment and the anatomical programming program are LUTs or lookup tables that are the expected baseline image. These lookup tables are shown on your captured image, and by adjusting the brightness and contrast you can scroll the H&D curve over the histogram that is shown to correct or change the contrast and brightness. As you increase the brightness, you actually are subtracting data from the image, and this can result in quantum model. This computer can manipulate the brightness level of the image regardless of the mask used in the exposure, but will suffer quantum model. You have a low signal-to-noise ratio. Next, we'd like to look at window width. Window width is reflective of contrast. Window width controls the image contrast, the range of grays the computer is able to display for an image. A wide window width has many shades of gray and a long scale of contrast, so it has low contrast. A narrow window width has very few shades of gray, so it has a short scale of contrast or high contrast. The greater the bit depth, the more shades of gray that can be shown. Now that we understand that, let's revisit using the histogram and moving the H&D curve over the histogram to change contrast. Here we see the image display along with the H&D curve over the histogram. Notice that the straight line portion is in the middle of the histogram. By adjusting the contrast and brightness, we can move that H&D curve over the histogram itself and change the exposure look on the display. Here we've moved the curve to the right, and you can see that the straight portion of the curve is over nothing, so we have a histogram that's going to be too light. Notice what happens when we move the H&D curve over to the left, and we make a more vertical slope on the H&D curve. We get a histogram that is too dark. The gradient of the slope actually controls the contrast. And we have very high contrast and over in the dark area. By flattening the gradient, we're able to show more shades of gray, so we have less contrast. With imaging processing, additional work is required before the output data from the image receptor is actually useful. Processing of digital images must be used to correct and adjust various image characteristics. Not only can we adjust contrast and brightness, but we can also zoom and magnify our images using image manipulation and by changing the number of pixels within a kernel. So let's finish up looking at algorithms and how we construct the image using lookup tables. Algorithms are all vendor-specific and proprietary, but they have one thing in common. They want DICOM in and DICOM out. DICOM is digital imaging communication, the standardized method used for manufacturers so machines can talk to each other. IHE stands for Integrating the Healthcare Enterprise and is how we use DICOM. Spatial resolution is how we map the intensities, the shades of gray which reflect the intensities of the radiation are mapped to the matrix to create the image. Here's an example of a number of shades of gray that have been mapped to create an image. Bit depth or pixel size also affect the shades of gray. Also, the amount of signal affects the image. The more signal you have, the clearer the image. As you start to lose signal, the image becomes starved for information and causes quantum model. The histogram is simply a two-dimensional bar graph of the intensities collected, but we can collect a different amount each time. The more data collected, the better the quality of the image. Produced by computing the frequency of the pixel values and is displayed as the frequency or number of pixels versus the pixel values. The values of the images are then inverted so that the areas of the high X-ray exposure appear to be black and areas of low exposure appear to be white. This process produces a negative image, which is the appearance of a film screen radiograph. On the right is the positive image that we've collected, and by inverting that, we get a radiograph that we're used to on the left. This completes the process of having a photon of energy interact with tissue to create a radiograph. The data from that interaction was utilized by doing an analog to digital conversion, which is taking the energy and converting it into numbers, and then taking those numbers or the data and reversing the process and converting the data into energy or visible light that's displayed on our monitor. Thank you for your time and interest, and I hope this has been beneficial in explaining how we create an X-ray image.